All right, everybody. Welcome to episode 2 of Quantum Honestly. I hope you enjoyed the introduction to some topics in quantum mechanics. And today we're going to continue talking and get a little bit more context and start digging into the subject more. And we're going to assume that you have no physics background here. And so we're going to talk today about a very easy quantum system we can describe, which is going to be a quantum coin, where we can get quantum superposition with just two numbers. So let's imagine that we have silver atoms fired through a magnet towards a glass plate. We'd imagine that we'd have a smearing effect that happens. Okay. But nature actually gives us an answer here, and it's two dots. And a perfect 50-50 can flip to 100% just by turning a detector. So these atoms are tiny spinning magnets pointing every which way. So on the plate, when we're firing through, we should get a smear, like a vertical smudge of some kind. But the two dots and the kicker here, we can make a coin that's a perfect 50-50. And then our detector in our experiment, we can turn it by 90 degrees without touching the coin, and it comes up 100% heads. Now we know no ordinary coin could have this property without touching the coin. Now, last episode we did something that sounds impossible, so let me catch everyone up. If you missed episode 1, you don't lose anything here. We fired tiny particles one at a time at a wall with two slits cut in it. Each one lands as a single dot. Tick, 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 like a thrown pebble. Particles, plainly. Now, but let thousands of them pile up, and the dots arrange themselves into stripes, bright bands and dark bands, the unmistakable signature of a wave. Each particle somehow interferes with itself. The question then becomes particle or wave. The answer is neither. It's a new kind of thing. And here's the part that should bother you. Pick one bright spot. Now I open a second slit. I give each particle more ways to arrive, and that bright spot goes dark. Adding a door removes hits. Opening a path made the screen darker. No marble, no water wave you've ever seen before has done that. And that one impossibility is the whole reason we're about to need a brand new kind of number. So how did episode 1 explain that? Well, with one rule, and it's the only thing you need to carry forward with you here. Riding along with each particle, there's a hidden quantity. And unlike an ordinary count, it can be positive or negative. We gave it a name, the amplitude. The rule is this: to get the odds of landing somewhere, you add up the amplitudes for every way to get there, and then you square the table. Watch why that actually cracks the case. 2 ways to arrive, each plus 1. Add them, you get 2. Square it, you get 4. That's a bright spot. But open that second slit, and one path now comes in as a -1. Plus 1 and -1 cancel to 0. You square it, it's still 0. Therefore, it's dark. The minus ate the hit. Add first, then square. But notice, a number on a line has only 2 directions it can face: forward or backwards, plus or minus. And that, it turns out, is too poor a language for the full story here. Those plus and minus numbers are really little arrows, and an arrow can point any direction, not just 2. Building that arrow is this whole episode. Now, one bridge between episode 1 and this episode before we go, because last time it was slits and today it's a magnet, and they look nothing alike. They're 2 faces of the same weirdness. Episode 1 ended with a promise that we build the machine on the simplest quantum system there is. Just 2 outcomes, 2 numbers. That system is today's coin. Now, here's the trap, and almost everyone falls into it, myself included, the first 10 times you see it. You think the quantum coin is like this coin, already heads or tails the instant it lands, and 50-50 just means you haven't peeked at it yet. The answer is sitting there, you're simply ignorant of it. That picture is comforting. It is also wrong, and by the end of this video, you'll be able to prove it's wrong with one twist of a magnet. And it feels familiar. It should. It's the very same trap from the last episode, just in a new costume. There we wanted to believe each particle surely took one definite path, and we just didn't happen to know which it was. It's the same comfortable lie in a new disguise. We'll meet this coin in a cup 2 more times in this series, each time dressed differently. So make sure to spot it every time. Now, remembering the magnet from the top of the show, the one that gave us 2 dots instead of a smear, let's stop being mysterious and look at what actually it is. Because every word coming up hangs on this one picture. It's a sorter. Atoms fly in, the magnet nudges each one up or down. It hits a plate and leaves a dot. A dot up top we'll call up, a dot at the bottom we'll call down. That's the whole machine. And it has a name, a Stern-Gerlach magnet, after the 2 physicists who first built it. You don't need the name, I'm just saying it once so it won't startle you later. Now, 2 things here to set up. First, the magnet sits on a dial, so I can rotate it. Standing straight up, I'll call that the Z setting. Tipped over onto its side, I'll call the X setting. And here's all Z and X are. It's just names for 2 dial positions. Nothing to decode. Now, quick note, sideways isn't a single direction. Like compass headings drawn on a tabletop, there's more than one way to point sideways. We'll mostly use up and down, Z, and one sideways, X, with a second sideways heading turning up a little later. Now, second, that silver atom is the, quote, coin I keep talking about. And the property this magnet sorts has a name physicists lean on constantly. That called spin. Now, heads up, though, and I mean it, it is not a tiny ball that is physically spinning. It's a loaded word, and we'll come back to it at the very end. For now, just think about spin as the up or down thing that the magnet itself reads. Okay, back to that cliffhanger. Now that we met the machine, remember the plus or minus amplitudes from the episode 1 recap? We're about to upgrade them, and here's exactly why they need upgrading. A plus or minus number lives on a line, and a line is a poor little world. From any point, you can only go 2 ways, forward or back. That's all positive and minus ever were, 2 directions on a line. But the thing that made those fringes, the thing that let paths reinforce or cancel by every shade in between, was direction. Richer direction than a line can actually hold. So we give our number a little more room. We let it live on a flat sheet where it can point not just forward and back, but any way at all. A number with a direction on a sheet, that's an arrow. And that one upgrade is the whole new tool. So let's actually look at one of these arrows. It's the simplest thing in the world. It has a length, how long it is, and a direction, which is the way it points. That's it. That's the whole object. Now, there are 2 equally good ways to describe the exact same arrow, and I want both in your hands. The first is the obvious one. Tell me the length and tell me its direction. The direction is just an angle, and mathematically we write that with a Greek letter theta. Don't let the letter do anything to you. Theta is just a name for which way it points. The second way uses shadows. You shine a light down from straight above, and the arrow throws a shadow on the floor. You call that how far east it reaches, for example. Shine a light from the side, and it throws a shadow on the wall. How far north? Give me those 2 everyday numbers, east and north, and I can rebuild your arrow exactly. And here's the thing not to miss in all this. Those aren't 2 different arrows. Length and direction are east and north. It's the same arrow described in 2 different ways. Like giving someone your location as half a mile that away versus 3 blocks east and 2 blocks north. It's the same spot. It's just 2 different ways to say it. Now, one bit of vocabulary here, just so it doesn't spook you later on. These point anywhere numbers have a real name. They're called complex numbers. That's really all a complex number is. It's not complicated. It's not imaginary nonsense. It's an arrow on a sheet with a length and a direction. Now, a quick reassurance here for anyone whose heart sank when those words, uh, when you hear cosine and sine showed up, because trig class was probably a long time ago, or maybe it never quite clicked for you. You don't need any of it here. Just remember our arrows, two shadows, how far east on the floor, how far north of the wall, and that's happened. All that's happened is that mathematicians gave those two shadows names. The floor shadow is what we call cosine, or cos for short, and then the wall shadow is what they call sine, or the sin for short. That's the whole thing. Cosine and sine aren't formulas to dread, they're nicknames for how far east or how far north as the arrow swings around. So whenever one flashes up on the screen, don't tense up, just hear the word shadow. Okay? Now, here we've got our arrow. Now meet one special arrow that does all the heavy lifting, and it carries a letter you've heard before and maybe learned to fear. I. Forget whatever imaginary number baggage that letter dragged up for you. Here is all it is. Point I is just the length 1 arrow pointing straight up, due north. And it has one magic trick. Multiplying by I is a quarter turn. And you can watch here. You can start with our arrow pointing east, times I, it swings 90 degrees, times I, 90 degrees again, and go around. So 4 quarter turns equals a whole circle. And now I can finally tell you why that north shadow gets tagged with an I. Because I is north. Anything pointing north is just I times how far north it reaches. So here is our arrow written out in full. Length R aimed at angle theta. Its east shadow is R times cosine theta. Its north shadow is R times sine theta. And that north piece rides on an I. Snap them together and you get the label Z equals R times, in brackets, cosine theta plus I sine theta. That's not a scary equation. It only ever says how far east plus I times how far north. Now, if that letter still feels like a magic trick, here's a demystifier, and it disarms the scariest fact about it. We just said times I is a quarter turn. So times I twice is 2 quarter turns. That'd be a half turn. And a half turn leaves you facing dead backwards. Now, what does times minus 1 do to an arrow? Well, it flips it around to point backwards too. It's the same move. So 2 quarter turns and 1 times minus 1 land in exactly the same spot. That is all I squared equals minus 1 is saying. Turn a quarter, and you flipped your sign. Nothing imaginary about it. That's just a rotation. Perfect. Now, here's the rule that runs all of quantum mechanics, and it's all about that arrow's length. See those bars around Z, the vertical bars? That's just shorthand for the length of the arrow. Its fancy name is the modulus, but it only ever means length. And here's the move. To get the odds of an outcome, you take the arrow's length and square it, or those vertical bars wrapped around the Z squared. Now watch the bar. The arrow swings through every direction and the odds never budge. Squaring throws the angle clean away. 2 arrows pointing completely different ways can share the exact same length squared. Hold on to that. It's the whole episode. And 2 quick footnotes here. That arrow is the amplitude from last episode grown up. The plus or minus number that could cancel at the slits. And to get its length from the 2 shadows, you use the right triangle rule from school. Pythagoras. East shadow squared plus north shadow squared. And since we wanted the length squared all along, we never even take a square root. The odds are just east squared plus north squared. Ooh, let's go on to the next one. There we go. Now, one more rule, and it's the one that cracks last episode's mystery here. Arrows add tip to tail. You lay the second arrow's tail right on the first one's tip. The trip from the very start to the very end is the sum. It's the same direction. The arrows just pile up. A long arrow, which means a bright spot. If it's opposite, they cancel. So they cancel to nothing, a single dot or being dark. That's the double slit interference from episode 1, except now it isn't hand waving, it's arithmetic. Add the arrows first, then square. And here's a name to file away. The arrow's angle, the direction it happens to point, has a proper name. It's called the phase. Now, phase is just which way the arrow points. Now, two cautionary notes here. This arrow isn't spinning anywhere in real space. It lives on an abstract bookkeeping sheet. And the phase isn't visible to any single measurement. Squaring throws the angle away, remember. You only ever feel the phase when two arrows add and either reinforce or cancel each other. The length you can measure straight off. The phase you can only catch in the act of interfering. Okay. A quick deeper cut because I just used one word, phase, for two different things. Now, in a minute or two, we'll build up our quantum coin out of two arrows, one for up and one for down. So just keep that in the back of your mind. There's a global phase, spin the whole state, both arrows by the same angle. And squaring always kills that one. So no experiment in the universe can ever catch it. But there's also a relative phase, a lone quarter turn between the two arrows, the angle of one arrow compared to the other. You'll meet it in a few minutes as the lone eye standing inside one of the two named states. Think of two singers, one for up and one for down. Delay the whole duet by a second and it sounds identical. But slide one singer half a beat against the other and the harmony either locks in or it clashes. That relative phase hides from the Z detector, but it jumps right out at the moment a detector makes two arrows add before squaring, which is exactly what the X detector does. Okay, now we're about to do a little bookkeeping here, and it needs a label. When a physicist wants to say the coin is in such and such a state, they don't write out a sentence, they draw a little container around the state's name. A straight bar on the left and a pointy angle bracket on the right. So inside you write what the state is. So where we have the bracket or the vertical pipe with the arrow up and the bracket, that means the coin is definitely up. And then for the down, that would mean that the coin is definitely down. That little container has a name. It's called a ket. It's an odd word, and here's a little story for you. It's a pun by the physicist Paul Dirac. There's a mirror image half called the bra, written with the bracket the other way around, and bra plus ket spells bracket. We'll need the bra later, the moment we start asking the coin questions. For now, let's just read the line with the arrow up in the angled bracket as the coin is definitely up. Nice. Now, so where does the ket actually live? Well, here's the friendly picture of a quantum coin. It's a list with two slots, a little labeled box. The top slot says how much up, the bottom slot says how much down. So definitely up is the list 1, 0. All the way up, nothing down. Definitely down is 0, 1. And if I set a number out front, it simply scales what's in the slots. A times 1, 0 drops the arrow A into the up slot and leaves the down slot empty. This list of two numbers has a real name. It's a vector, but the two slot list is all it ever means. Now, I have to wave a big red flag here because we suddenly have two different twos in the room and they are dangerously easy to fuse. A few minutes ago, one arrow had two shadows, how far east and how far north. One object described by two numbers. This is a different thing entirely. Here, each slot holds its own arrow, a complete up arrow in the top, a complete down arrow in the bottom. Two arrows now, not two shadows of one arrow. Keep those two ideas in separate pockets, and the rest of this episode will be easy. Okay, now the payoff, and it's the whole reason you built those two slots. A quantum coin has a real name. It's a qubit, which is short for quantum bit. And a qubit is just two of those arrows, one sitting in the up slot and one sitting in the down slot. So you see here we have this psi here for our state, okay, the whole state, and we give that with the letter psi, is just a label meaning the coin right now is amount of up plus is a amount of up plus b amount of down. A is the arrow in the up slot, B in the down slot. Stack them and you get a list of bracket A comma B. This is a genuine blending of up and down, not a list of maybes, but truly both at once until you look. And it has a name called a superposition. That one word is the whole game. And the two arrows aren't free to be any old length. You square each one's length and add them up, and you get exactly one. Because the coin always lands somewhere, up or down, it never vanishes. So a squared plus b squared equals 1. We'll lean on that so often, I'm dropping it right here. Just make sure you remember that, okay? Now, here they are, A and B, two arrows. The two numbers I promised you at the very top of the show. One bit of care with the head count, though. Each arrow counts as one number on that flat sheet. Don't go back and recount its east and north shadows. Two arrows, two numbers, one coin. Now, let me put two specific coins on the table, the two we'll use for the rest of the episode. Here we have plus X and plus Y, okay? And don't let the name spook you. Plus X and plus Y are just two more definite settings of our coin, okay? The two sideways headings of the magnet I mentioned earlier. The one 90 degrees apart, like east versus north on a tabletop. Definite directions, same as up and down, just lying on their side. Now you notice there's a 1 over square root of 2 in front of both of these. Now, that's a normalizer. It's there to keep the squared lengths adding to 1 so the odds behave. I'll show you exactly where that number comes from on the next slide. For now, just read it as the factor that makes the odds add up. Now look closely. Our state of plus X is 1 over root of 2 times the list 1, 1. Our state of plus Y is 1 over root of 2 times 1i, that state. And there's that quarter turn I showing up again, sitting in the down slot. So it's the same lengths as the positive X state, just different directions. Remember our load-bearing rule here. Squaring kills the direction. File that away. It's exactly the trap we're about to spring. Now, one bit of vocabulary while we're here, you flip the sign of that I and you get the arrow's mirror image written with a little star after the A. Mathematicians call it the complex conjugate, but mirror image is a fine enough term for us here today, and that's kind of what it is. Same arrow reflected. It does nothing to a plain number with no I, so the state of positive X won't even notice it. But the instant an arrow carries an I, the mirror flip earns its keep. For instance, when we check the positive Y, its own add to 1, the I over square root of 2 squared equals a half. And the star is what makes that come out as a clean positive half. Now, we'll do exactly this by hand in just a minute. Now, a quick little optional step off here. Where does that 1 over root of 2 actually come from? It's not a magic number. It falls right out of our odds add to 1 rule. We want our state of positive X to be a fair even split, equal up and equal down. So you start with the simplest even pair, that of 1, 1 in each slot. But square the lengths and add 1. Obviously, that ends up to be 2, not 1. It's too big. So we shrink both arrows by just enough to fix it. Divide each by root of 2, which is simply the number whose square is 2, about 1.4. Now each slot holds 1 over root 2. Its square is a clean 1/2, and a half plus a half is 1. Therefore, your odds have been restored. And that's all that little factor ever is. The shrink that keeps a fair coin honest. One thing here, though, 1 over root 2 is not a half. It's about 0.7. It's the square of it that's a half. The arrow's length is 0.7, and the odds are a half. Now, if that I in the Y state made you nervous, here's the reassurance, and it's the very number we just flagged. The squared length of any of these arrow numbers is just its length squared, and a length is always a real non-negative number. So a probability can never come out imaginary or negative. The I is an arrow of length 1 pointed straight up, a pure quarter turn. So I over root 2 is an arrow of length 1 over root 2. Square that length and you get a clean half. Picture us spinning a pencil flat on a table. East, north, northeast. It never changes how long the pencil is, and the probability is the pencil's length squared, not where its tip points. The I only sets the direction, and direction is exactly what squaring throws away. So we've built the coin. Now how do we read it? How do these two arrows turn into actual odds for a specific detector? Here's the recipe, and we start with the plain English handle before any symbol. It's all about overlap, how much one arrow pair points along another, like your coin up against the outcome you're asking about. See how much they overlap and square it. That square is your odds. Now let's give the outcome a name. The Greek letter phi is just the result we're testing for, like land up or lands positive x. To ask the coin how much do you look like phi, we turn that outcome into a question. And we write the question with the flipped brackets, where you have the angled phi and then the vertical pipe. Remember Dirac's pun earlier, the vertical bracket, vertical pipe psi bracket was the ket. This question half, the angled phi pipe is the bracket. Push them together so you end up with the angled phi vertical pipe psi bracket, and you've literally asked how much of psi looks like phi. And the recipe to compute it is short. You multiply the matching slots using the mirror image of the first one and add. Mirror the outcome slots, line them up against the coins, multiply across, sum. That's the overlap. And then you square it, and out drops the probability. P is equal to the question there, the phi psi squared question. This rule, this overlap then square, has a name. It's called the Born rule, after physicist Max Born. It's the single bridge between the arrows and anything you actually measure. Okay. Now, why square exactly? Why does just looking force the coin to pick at all? Those are the two deepest questions in the whole subject, and they get their own episode. That's episode 3, and so next one. Today, we're not going to ask why. We just use the rule and watch it do something a normal coin simply cannot. Now, why bother with that mirror flip, and does it even matter which arrow you flip? It does, and here's the tell. Flip the sign of the I in the first one, and then multiply the matching slots and add. Do it to a state against itself, and the mirror turns the sum into A times A plus B times B, which is the length of A squared plus the length of B squared, which is a real number that equals 1 for a normalized state. Dead certain, exactly as it must be. It's the complex cousin of taking a distance, maybe A plus B of I times A plus B of I, which is A squared plus B squared, always positive because the mirror copy squares away both the sign and the angle. Take our positive Y state for a concrete case. Its down slot, A times A, is 1 over the root of 2 squared. A clean plus 1/2, whereas without the flip, you get I over root 2 squared, which is minus 1/2. Okay, now without that conjugate, it's the minus conjugate 1/2. Without that conjugate, rotating a state by I would flip its own overlap negative, and a negative probability is nonsense. Okay, so we've built the coin, and we've got our Born rule for reading it. Okay, let's actually turn the crank. Two states, A is equal to positive X and B is equal to positive Y. We'll grind the numbers by hand first, then check ourselves in code. So what we do is we normalize both. A half plus A half plus A half is 1, which checks out. And for B, the I is a length 1/4 turn. So I over root 2 squared is a half 2. You measure along Z, up versus down. A is 1 over root 2 squared, which is a half each way. B is 1 over root 2 squared for up, and I over root 2 squared for down. A half each way too. Now, these are identical. It's 50-50 for both. On Z, these two coins are completely indistinguishable. Now you rotate the detector to X. A is exactly plus X, so the overlap is 1. So the probability of plus X is 1. It's 100%, dead certain. But B against positive X comes out 1/2, because that was 1/2 plus I over 2. And since that's an arrow with sides 1/2 and 1/2, Pythagoras gives us 1/4 plus 1/4 equals 1/2. Still 50-50. Okay. Now, here it is. Two coins that are the same on one detector Z, where they're both a clean 50-50, and completely different on another X, where one is dead certain and the other is still a coin flip. Okay, so you see there's Z, and then one is certain, one is a coin flip. Now, sit with that for a second. An ordinary coin in a cup has one definite answer sitting there, already written, just waiting for you to peek. And a written down answer reads the same no matter which way you turn to look at it, correct? Now, these two cannot do that. So the answer was not written down in advance. The hidden answer picture is dead. Now, here's why the two detectors are allowed to disagree. A Z measurement just reads the two arrow lengths separately, A squared plus B squared. It never puts the arrows together. So the angle between them can't possibly matter, and both states come out a half each way. But X asks a different question. You have to add the two arrows first, and only then can you square them. Now the angle between them, the relative phase, lives right inside that sum. For positive X, the state of positive X, the two arrows point the same way, so they add to a full overlap of 1, 100%. For the state of positive Y, the quarter turn I tips one arrow, so they add to a half plus I over 2, whose length squared is only a half. Okay. Now, picture, we have two solid objects throwing the same shadow on the floor, but different shadows on the wall. Same on one screen, different on another, except here's the catch that makes it quantum. The qubit isn't a hidden solid object you're actually uncovering. The axis you measure along doesn't reveal the answer, it actually creates the answer. Let's not take my word for it. Here's our toolkit. I build both states and fire each one through a virtual Stern-Gerlach magnet. That same sorter we met back at the top of the show. And I go through and I do this 10,000 times. Okay. Both histograms land about 50-50 on Z. Okay. Exactly like I said when I worked it out for us. Now we rotate the magnet onto X. Okay. You see, and A snaps to 100 while B just sits there at 50-50. The misconception dies on these histograms here. And here's the cleanest way to see why these two are different. It's something called the Bloch sphere. Now, every qubit is a single pin on a globe. North pole is up, south pole is down. The equator is a perfect 50-50 on Z. And the longitude, how far you've walked, is that arrow's direction, the phase of it. This globe has a name called the Bloch sphere. Now let me close a loop that might be nagging you. All episode I've said a qubit is two arrows, A and B. So why does this globe need only two real numbers, latitude and longitude? Some of what's tucked inside those two numbers is simply invisible. The overall spin of the whole pair, no detector in the universe can catch that. Plus a little slack that vanishes the moment we force the odds to add to 1. Strip those away, and all that's left to pin a qubit is two dials. The latitude, which is your Z odds, and the longitude, which is the phase. Okay? That's literally why the Bloch sphere is a 2D surface, a globe you walk on, not really a solid ball. So let me actually drop our two states onto it. Let's do that. There they are, both sitting on the equator, but a quarter turn apart. Same latitude, that's why Z can't tell them apart. Different longitude, that's why X can. Same odds, just a genuinely different state. Okay. Now, quick honesty note before we wrap. The angle in the math is half the angle you turn the pin on the globe. That's the theta over 2. Up and down sit a full 180 degrees apart on the globe, yet as arrow pairs, they're a 90-degree right angle. There's a genuinely wild consequence of that factor of 2 when you spin a qubit a full 360 degrees, and it's so good it gets its own primer. Now, remember way back when we met the magnet, I flagged the loaded word called spin and promised we'd come back to it. Well, here's the payoff. The spin is an intrinsic label the particle carries, not a tiny ball physically rotating. The tell is that it takes a 720-degree turn, not 360 degrees, to bring it home. Nothing that actually spins in the everyday world does that. We kept the word spin, the spinning picture, we did not. Now, one more thing on that half angle, because it trips everyone. Up and down are the two most distinguishable states there are. And perfectly distinguishable means orthogonal. A 90-degree right angle overlap would be 0 in that case. Yet on the globe, they sit at opposite poles, a full 180 degrees apart. The globe simply doubles every angle. The math angle between the arrows is theta over 2, and what you walk on the sphere is the full theta. It's a steering wheel geared 2 to 1 to the tires. Crank the wheel a full 180 and the tires turn only 90. The globe is the wheel, the real state is the tires turning half as much. Okay, so what we did, to wrap up, a quantum coin is two spinning arrows that have mixtures of A and B. Squaring a length gives the odds, and squaring throws away the direction, which is exactly why two states can match on one detector and split on another. We proved the hidden answer coin is wrong picture using nothing but 1/2 plus 1/2 equals 1 and 1i. But we cheated twice. We used square the amplitude without ever saying why, and we never explained why looking forces the coin to choose it all and seems to change it. That's measurement, the Born rule, and collapsed. And that's what we're going to cover next time on Quantum Honestly.